We're now going to start the problems on electrochemical batteries, which really I find very simple. Once you did all the rest, this is a piece of cake. These are all number question 13 to 18. I'm going to go fairly quickly because you already know how to do everything. And just because the cells are separated in an electrochemical battery, but the reactions and how to calculate the delta E, the E on the both electrodes is the same as if they were in the same solution. Okay. So consider the two half reactions, half cell A and cell B. Okay, A, they said, is composed of a silver blade immersed in a solution which contains Ag plus ions, and they gave you the concentration of the Ag plus ions. B is assembled by dipping a platinum plate, an inert plate, into a solution of tellurium plus and tellurium 3 plus, and they gave you the concentrations. Now, the first thing you notice, these concentrations, of course, are not at equilibrium, and they are not 1 molar, and therefore we are not under standard conditions. Now they say when the circuit is closed, the EMF of the battery is the following. EMF is E of the cell, in other words, equals plus 0.54 volts at 25 degrees Celsius. And they're telling you that the silver electrode is the negative pole of the battery. The idea right away, even if I don't tell you that that's the anode, the negative pole of any battery is the anode. And what does that also tell you? That it's the oxidation reaction, the oxidation at the anode occurs. So the silver electrode is going to undergo oxidation. Questions, draw the scheme, okay, and the electron flow. Write down the equation of the overall reaction and get the E node, because they didn't give us one of the E nodes for the silver. They gave us the E node of the silver. They want you to get the E node for the tellurium and calculate the K of the reaction at equilibrium. So first, we know that the silver electrode is the negative pole of the battery. Great. And the idea, why did they say it under a closed circuit, the EMF is the following, plus 5.4? They said that because once the circuit is opened, guys, we're no longer able to relate the E or the delta E of the cell to the concentration term, okay? So because they're only related to work and thus to delta G only when the circuit is starting, right at the beginning, or when it's closed. It hasn't really, that's the maximum for the cell. Okay, so the negative pole is the silver, and therefore the negative pole is where oxidation occurs, and then you get the positive pole where reduction occurs, and therefore we're done. The Ag pole is on the oxidation. It's inserted in an Ag plus solution, and we have tellurium on the reduction side, and since both are ions, we need a platinum neutral plate as my electrode. And that's the diagram of the battery, okay? Now, if I want it in terms of a cell diagram, we can write it down, of course. What do? You put the oxidation here, you put a double line, for the salt bridge, and the reduction side on the right-hand side. So you start with the oxidation. And how do you write it down? You write it down as it's written in an oxidation form. So it's the Ag solid becomes Ag plus. That's an oxidation reaction. Write a straight line to separate solids from ions or aqueous solution. And beside the ion, you should always have its concentration in brackets, okay, with a molar sign. On the other side, we have tellurium and tellurium plus. Sometimes they don't really worry about which one they put first, but it's always better to put them in the form of a reduction. So the 3 plus ox becomes the red, the less cationic. because this is the order that they come in the reaction of a reduction. These are separated by commas, okay, and each of them has its concentration term in brackets. They're then separated by a platinum straight line. Okay, they're separated by a platinum straight line because the platinum is the solid. And you are done. That's the cell. You can put minus plus here to show that this is the negative pole and that's the positive pole of my battery. Okay, when these are assembled to an external wire, you adjust it to a voltmeter, then the electrons flow, of course, from the aux to the, so the electrons flow from the aux side, negative pole, through the voltmeter to the positive pole, okay? So there's the electron flow. And how about the other side? The current. How does the current flow? Conventionally, guys, it's always opposite to the direction of the electron flow. So the current goes from the positive pole to the negative pole. And here we say, this is formally, that the direction of an electric current is by convention the direction in which a positive charge would flow. And a positive charge would start at the positive pole and go to the negative terminal, which is opposite to the electron flow. Okay, so write down the overall redox equation. Well, we already know that on the reduction side, we have the tellurium, half cell B, which occurs at the cathode, and therefore write the reaction as a reduction. On the half cell A, we have the oxidation where it's the Ag couple, and write that in the form of an oxidation reaction where the electrons are on the product side. Then we should balance this oxidation with the same electrons as the reduction, so we have to multiply it by 2. And once we have that, we can add the two equations to get the overall global reaction. Here, clearly, there's no oxygens, no hydrogen, so I don't, very easy to balance. Now, knowing that the anode of the silver electrode with the silver ion ox red is 0.8, calculate the anode of the tellurium, okay, couple. This is a little bit harder, and that is, I don't have the anode value, okay? How can I get anode? Well, if I have delta E of the cell, or E of the full cell, I can get the anode. Can I get the E of the cell from somewhere? Well, I have the redox reaction, and if I have the reaction, and they gave me E of this battery when it's fully closed, that means I have this E or delta E of the cell. Now I prefer to call this delta E, and I'm gonna change this, well, or, with the Nernst equation again, for the overall reaction, we can call it E of the overall reaction or delta E of the overall reaction. So here is my Nernst equation for the overall reaction. And notice it looks exactly the same as for a particular electrode, right? It's in the same format, except instead of log of Q, well, it's still log of Q. It's exactly in the same format. And I was asked this question many times. The people are getting confused about the Nernst. Nernst, guys, is simply a relationship between E, the potential, related to a concentration term, which is Q. And so we can get any potential at any concentration, okay? And usually we started off at an initial concentration because that's when we get the relationship between potential and concentration. Okay, so E of the cell is E naught of the cell minus 0.0592 divided by the total number of electrons transferred for the cell. Log of products divided by reactants. And here's your products, each to the stoichiometric number. And that's it. Now we have E of the cell, that I have. Okay, so I can easily get the E node of the cell, okay? And so we can solve that because now it's like the opposite. Usually we want to find E of the cell. This time they already gave us the E of the cell, okay? The electromotive force, they gave it to us. And we have all the concentrations at initial states, you know, when the cell is fully closed. And therefore, E of the cell, put E of the cell on this side. Okay, take all of this term to the other side. This becomes a plus. We're still products divided by reactants. Are we clear? And solve for E naught of the cell. You get E naught of the cell is 0.45. So E naught of the cell is 0.45, and that is E naught of the cathode minus E naught at the anode, or E naught reduction minus E naught oxidation, or E naught at the positive pole minus the E naught at the negative pole, as you wish. Reduction is the tellurium, oxidation is the Ag, and so the delta E naught of the cell we just calculated, and so we can easily get E naught of the tellurium, which is delta E naught of the cell, plus E naught of the Ag. And you're done. Notice, why did I call this delta E naught? Again, I'm calling it delta E naught because I'm using this delta E's. Don't be confused. This delta E naught is the same as this E naught of the cell. It's the same number, okay? It's the same number. Just when we use Nernst, you know, sometimes we put it in terms of the E of this reaction. Okay, make sure, sit down, stop this slide, and make sure that you actually know how to solve this before moving on. Ask me any questions about it, because it will come up often, and this is one of the harder things to do. Calculate the rate constant at equilibrium. Well, this we've done often enough. The log K is N times delta E naught divided by 0.52, and it's always delta E naught, even if you are under non-standard conditions, okay? The total number of electrons transferred is 2, or you could say 1 times 2, because it's the N transferred for each half cell. The delta E naught, we calculated to be 0.45 and 0.592. It is the division. Log K is 15.2. Get the K, 10 to the power of this number. And you notice that it's a fairly high number, and the reaction is therefore more or less complete. Okay, so again, watch out for the number of electrons in this equation. It's the total number of electrons transferred in the redox cell. Next question, number 14. Consider the following cell: lead, salt in a lead ion solution of 1 molar, salt bridge, iron 1 molar in an iron 2+ on a platinum plate. Okay, so what is the cell? Well, yes, everything is in 1 molar, so it's under standard conditions already. That's fine, that's great. They want us to write the half reactions occurring at the 2 half, assign the polarities, calculate E, and so on and so forth, a bunch of questions. And they gave us the E naughts. How lovely, how easy. They gave us the E naughts for both couples. Okay, so we're under standard state automatically. What can I do? Of course, to have the reaction. So now, indeed, on an E naught scale, because everything is under standard conditions, we could easily find out which reaction will undergo oxidation and which will undergo reduction. The one with the higher reduction potential will undergo reduction, and the one with the lower reduction potential will undergo oxidation, and the iron 3+ will react with the lead as a spontaneous reaction. And indeed, even without this, we can see from the cell that the lead, of course, is my oxidation, because it's on my left-hand side of the cell, which falls right in the order of a spontaneous type reaction. So we have to write the half equations of occurring and the polarity. So here's the half equations. On the cathode, we're gonna put the iron, and that's gonna be our reduction half reaction, and that's my iron. On the anode side, we have the lead, and therefore that's my oxidation, and that is my lead in the form of an oxidation reaction. Now again, guys, you just put Fe2 plus, Fe3 plus, Fe2 plus, balance the electrons, 1 electron. Now, if you put them in a different order, just make sure as a reduction, the electrons are gained. So they're on the left-hand side here. So you add electrons. In the oxidation, make sure they're on the product side, the electrons, okay? So make sure you write them properly. Okay, we balance the two reactions, multiply the upper by 2, and get a global reaction by the electrons are now balanced, add the two equations, and we have an overall reaction and the two half reactions taking place at the two anode and the cathode. Part B, assign the polarity of the electrodes. Of course, we have the positive pole occurs on the reduction side, and the negative pole is on the oxidation side. That's my polarity of the electrodes. Calculate the E of the cell. Now, okay, this cell has an E. Let's say, what is this E of the cell? Well, E of the cell is E naught of the cell minus 0.0592 divided by the total number of electron transferred, which is 2 log of products divided by reactants. The typical Nernst equation for this cell, okay? Now, if I substitute here, what do we get for the E of the cell? Sorry, what do you get? Well, the iron is 1, the lead is 1, the Fe is 1, and therefore the E of the cell is simply the E naught of the cell. It's the same. Okay, so E of the cell is the E naught of the cell. So E naught is cathode minus anode, which is 0.9, because we already have the E naughts for both the lead and the iron, so that's 0.9. If you had solved it here, you get also 0.9. This is E naught of the cell. So E of the cell is simply equal to the E naught of the cell as we anticipated. Okay? Fine. Okay. Now, what is calculate the equilibrium constant K of the overall reaction that occurs inside the cell. Now, the equilibrium constant is, again, this expression, log K is N delta E divided by 0.92. The N is the total number of electrons transferred in the reaction. The delta E naught is always delta E naught. If I said delta E in a moment, I'm mistaken. This is always delta E naught. E cathode, E naught cathode minus E naught at the anode, or reduction minus oxidation. Solve, this is now number crunching, do the calculation, and log, you get the anti-log 10 to the power of the 30.4. You get the K to be this number, which is something 10 to the 30, which is very, very high, which is definitely a complete reaction. Now, this is a little bit harder, not too much, but they are asking you to deduce the concentration of the various constituents present at equilibrium, okay? Now, before I do that, I have to, if they don't ask you for K of the reaction, you have to find the K of the reaction, okay? If you want concentrations at equilibrium, you need the equilibrium constant first. We did that in the previous part. Initially, I have 1 mole, 1, everybody is 1 molar. When the reaction proceeds, it's minus 2x, plus 2x, and plus x. That's my concentration at equilibrium, okay? But since the reaction is complete, of course, the 1 minus 2x here, which is my only reactant, which matters in the equilibrium constant, since lead is a solid, this part, the iron, will become 0 because it's a complete reaction. Solve for x. X is going to become 0.5. Or take the iron concentration divided by 2. That is simply the same. Yeah. And you get the amount reacted is 0.5. Okay, so substitute in to get the equilibrium concentrations, and voila, 0 on the reactant side. The product, if you put for x 0.5, you get the iron 2 plus is now 2 molar, and the lead is 1.5 molar. Another thing, watch out for this table. Everything has to be in concentration and not in moles, guys. Better to be in concentration because I'm substituting into an equilibrium constant K. If I was substituting it into a Nernest equation or into something else, I can keep it in moles. But here, I'm substituting it into an equilibrium constant. Okay. So we have the iron 2 plus concentration, we have the lead 2 plus, and we want to calculate the concentration of iron because we know all the species. But iron 3 plus is 0. Well, there's no such thing as 0. Remember, 0 is really coming, there's always a back reaction. So there's always minus here, 2 epsilon, we call it, minus epsilon and plus 2 epsilon. So here there's, an epsilon term. But remember, if the reaction is complete in one direction, it's limited in the back direction. So here we never really put minus 2 epsilon. There's no need. Just that the iron, we can leave it in terms of epsilon. I like to keep it in terms of, this is the concentration of iron 3 plus. That remains. So the iron 2 plus we have, the lead 2 plus we have, and I want to find the iron 3 plus. How do I find it? I find it from the equilibrium constant K because I have everything else in my solution. And since I have K, I can get the Fe3 plus concentration. K is the equilibrium concentration of the reactants, of the products divided by the reactants, each to its stoichiometric ratio. And then it's mathematics. Solve for Fe3 plus. You have the K, you have each of these, get the Fe3 plus, and that's the number that you get. Okay, I'm gonna stop this recording.